In this problem, we're told that the power absorbed by the box below is P of t is 2.5 e to the minus 4t watts. We're asked to compute the energy and charge delivered to the box in the time interval 0 less than t less than 250 milliseconds. We can see our voltage source there is 50 e to the minus t volts. We've got the current labeled. And to start, we know, for instance, the energy is the integral of the power. So when we get ready to calculate the energy, all we have to do is integrate the 2.5 e to the minus 4t. If we're going to find the charge, we know that Q of t is the integral of I dt, which means that we're going to need to calculate the current I. We know that P is equal to V times I. So then I is P over V. So we have 2.5 e to the minus 4t divided by 50 e to the minus t. That gives us a current I of t 0.05 e to the minus 3t amps. So now, first let's calculate the current, or the charge delivered to the box in the time interval 0 to 250 milliseconds. So we have Q is the integral from 0 to 0.25 of 0.05 e to the minus 3t dt. And if we integrate that, we'll get 0.05 over minus 3 times e to the minus 3t, evaluate from 0 to 0.25. And we'll have 0.05 over minus 3. We'll have e to the minus 0.75 minus e to the 0. And if we pull this minus sign in, we'll have 0.05 over 3 times 1 minus e to the minus 0.75. And if we calculate that, we'll see that it's 8.8 millicoulombs. Now we need to calculate the energy delivered in that time interval. So now we'll have the integral from 0 to 0.25 of 2.5 e to the minus 4t dt. So integrating, we'll have 2.5 over minus 4 times e to the minus 4t, evaluate from 0 to 0.25. So we have 2.5 over minus 4 times e to the minus 1 minus e to the 0. And if we take the minus sign in, we'll have 2.5 over 4 times 1 minus e to the minus 1. And that's 395.1 millijoules.